Hey everyone, welcome to BCP Med. In this video, we are going to go over the definition of ionization energy, what factors influence the magnitude of this value, and the associated periodic trend. We are also going to look at the interesting cases of group 13 and group 16 elements. Let's go ahead and get started. What exactly is ionization energy? Formally, it is defined as the amount of energy needed to take an electron from some energy level n and move it to the energy level n equals infinity, which is the energy level where the electron is completely removed from the atom. If we go ahead and look at an energy level diagram for an atom, we can consider ionization to be the motion of the electron from, say, the n equals 2 energy level to the infinite energy level, as indicated by this red arrow, right? We're moving from n equals 2, a finite level, towards n equals infinity. Because this transition is moving upwards in energy, it's going to require some input of external energy to accomplish, as indicated by this squiggly yellow arrow attacking the electron here. That energy can come in many forms, such as heat, radiation, or even electrical potential energy. The exact amount of energy needed is simply equal to the difference in energy between the infinite energy level and the energy level you begin at. And that is going to be described notation-wise as delta E sub I, or the ionization energy. Of course, in this case, the infinite energy level is a little bit of a misnomer, because the energy of the n equals infinity level is actually zero, or zero potential energy, whereas the energy of the n equals 2 level is negative, since the electron is attracted to the nucleus. So to ionize, what we're really doing is simply providing an input of positive energy equal in magnitude to the negative potential energy of the starting level. That is going to be our E sub I, our ionization energy, the energy required to remove a valence electron from an atom. Now, there are two main factors that influence the magnitude of the ionization energy. The first is going to be the effective nuclear charge acting on the given electron. We know that the potential energy of an electrical system is going to be given by U equals Q1 Q2 over R, or rather K Q1 Q2 over R. So the potential energy of an electron is going to be directly related to the charges involved, where one of the charges is just the electron charge, and the other is the nuclear charge, which I've circled here in red. But in reality, the electron doesn't ever actually feel the full nuclear charge, only the effective nuclear charge. So Z effective is going to determine our potential energy, and since ionization energy is simply the same magnitude as the potential energy, it determines that as well. For example, consider these two atoms. One has a Z effective of +1, like an alkali metal, and the other +7, like a halogen. The one on the right is going to have a higher ionization energy because the nucleus is going to lead to a larger potential energy well for that electron, and therefore more energy will need to be put in to release that electron or ionize it to the n equals infinity level. So the one on the right is going to have the higher E sub I. Another factor that is going to influence it is the radius of the atom, right? There's a radius correlation as well. The potential energy equation shows us that the energy is inversely proportional towards the radius of the atom. So the larger that the atom is, the weaker the attraction is and the lower the ionization energy. So if we compare these two structures here, the atom on the left, being larger, is going to pull on its electrons more weakly. It's going to have a lower binding energy for those electrons. A lower binding energy, or a lower potential energy, however you want to phrase it, means less energy needs to be input to ionize the electron, a lower ionization energy. So the one on the right is going to have a higher ionization energy as a result. So again, inverse correlation with radius, and a positive correlation with effective nuclear charge. Larger effective nuclear charge, higher ionization energy. Alright, so what are the periodic trends going to look like for ionization energy? Well, this periodic table shows ionization energy values for all of the elements quoted in megajoules per mole. Now, clearly, as you move towards the right-hand side of the periodic table, the values are increasing. We go from 0.5 on the alkali metals on the left to about 1.7 for fluorine, 1.3 for chlorine on the halogen column on the right-hand side, which is a substantial increase. It's about 1 million joules per mole from the left-hand side to the right-hand side. This is due to the increase in effective nuclear charge towards the right-hand side of the periodic table. As Z effective increases towards the right, the attractive potential energy of the electrons is greater, and more energy is required to remove them. Similarly, ionization energy tends to increase up the table. As the atomic radius gets smaller, the smaller elements at the top with fewer energy levels hold their valence electrons much tighter than the larger elements at the bottom. Hence, ionization energy increases up the table since we know it's inversely proportional to radius, as we discussed on the previous slide. It is also true that radius decreases from left to right due to the increase in Z effective, which is also contributing to the increasing ionization energy. At this point, I also want to point out an oddity that occurs here on the table. You'll notice that boron and oxygen have unusually low ionization energy values as compared to the elements around them. This is going to be explained more later. I just wanted to point out the fact that this is not a mistake in the table. This is a real anomaly that happens in these elements. Now, I want to turn our attention to what happens if we take more than one electron off of a given atom. Well, ionization is going to create a cation, a positively charged ion. This resulting positive charge is going to lead to an even stronger attraction by the nucleus for the remaining electrons. Right? As a result, the next electron is always going to be harder and harder to ionize off than the previous electron. For example, if we look at beryllium, which is represented by this Bohr model below, its first electron will come off relatively easily with an input of energy. Its first ionization energy is around 900 kJ per mole. However, due to the creation of a net positive charge, if we move now towards the Bohr model for the Be plus ion, its next electron is going to be much harder to take off. This time, the ionization energy, or the input of this yellow squiggly here, needed is going to be around 1757 kilojoules per mole, almost twofold increase from the first ionization energy. So it is always the case that the second ionization energy is going to be higher than the first ionization energy. Now, after we remove the second electron here in this step, something really interesting happens. Because the whole valence level is gone, we've removed the entire valence level and dropped down to the next energy level from n equals 2 to n equals 1, the effective nuclear charge has dramatically increased, right? Any further ionizations are going to have to start coming from a lower energy level, and these are held far more tightly by the nucleus since they have much less shielding, which is why we experience a higher effective nuclear charge, and they're also just closer to the nucleus, so the binding energy is going to be stronger in terms of radius as well. As a result, the third ionization energy of beryllium, aka the amount of energy to remove this next electron, this third electron, rockets upwards to almost 15,000 kilojoules per mole. This is a practically unreachable energy in normal environments, and so it's extremely odd to see any atoms ionize past their valence level outside specialized laboratory conditions. This trend of increasing successive ionization energy is true for all elements regardless of their position on the periodic table. Now, I want to dive into the group 16 and group 13 exceptions. I want to go ahead and start with the group 13 ones. We know that typically ionization energy increases from left to right on the table, mirroring the effective nuclear charge increase. However, we see from our data here that the boron atom actually has a lower ionization than beryllium, despite being further to the right. This occurs due to the fact that energy levels are not actually homogeneous. They are made up of distinct orbitals and distinct sublevels. And so if we look at the energy level diagram for boron, it turns out that removing an electron from a p orbital is going to be a bit easier than removing one from an s orbital. And so removing the lone 2p electron from boron is easier than removing a 2s electron from beryllium, because the 2p electron is sufficiently higher in energy than the 2s electron to counterbalance the increase in effective nuclear charge. As atoms get larger, the energy difference between p and s shrinks a little bit, and the drop between groups 2 and 13 diminishes. And so we see less of a discrepancy as we move down from boron to aluminum to gallium. However, between beryllium and boron, there's actually a substantial energy difference. Group 15 is going to have a different trend, but the result of the trend, in other words, is the same. Right? Oxygen is further to the right, but has a lower ionization energy than does nitrogen. Why is that the case? Well, it turns out it has to do with the elimination of electron-electron pairing repulsions. Right? We know that electrons don't like to be around each other because they're both negatively charged and they want to repel. This is why Hund's rule of electron filling exists to begin with. So if we look at the orbital diagram for oxygen, we see something interesting. In its p orbitals, it has one set of paired electrons. Wouldn't it be nice if we could get rid of that pairing and let each electron have its own orbital? In fact, this is exactly why oxygen has a lower ionization energy than nitrogen. Oxygen is willing, or more willing, to give up an electron to eliminate that repulsion between the electrons to alleviate the energy state of the atom. And so in this case, removing an electron from nitrogen would involve removing an unpaired electron, whereas removing one from oxygen removes a paired electron. So, like the other trend, this effect diminishes as you move down the periodic table because as orbitals become larger, the electrons have more space to move around, and the repulsions decrease. So it's not as substantial as an effect anymore. However, at the period 2 elements, where the orbitals are quite small and tightly held, those repulsions are a big deal and actually outcompete the effective nuclear charge for the increase in ionization energy. Finally, I want to go ahead and just summarize why ionization energy matters. First and foremost, it tells us how easily an element is to ionize and to be made into a cation. This tells us how metallic or non-metallic an element is going to be in its behavior, as metals are characterized by their ability to lose electrons easily. It also tells us the ability of an atom to be a Lewis base, aka an electron donor. As the lower the ionization energy, the more reactive electrons become to other species. It also informs us of the reduction potentials in electrochemistry, which is hugely important, and also gives us insight into the spectroscopic signatures of elements, which is essential in identifying compounds. Overall, it's an extremely important property and characteristic of a given element and its traits. And with that, we've reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. Make sure you check out our other videos in the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlist as well. See you next time!